Hello, everybody. Welcome to episode number 31 of Everything Playbook. Thank you so much for listening. I have a fantastic guest for you today. For those of us who follow geopolitics and modern warfare, the term directed energy weapons comes up more and more. But the technology behind it is so guarded that it is genuinely difficult for most of us to understand where does it actually stand, how far it has been developed, what is it truly capable of, and who are the people behind it. Any subject I choose to bring into this podcast, I want to go directly to the people who are physically handling that subject, the minds who are actively working towards the evolution of it, who are in the lab, who are living and breathing it. And one of those people is my guest today. Dr. Edl Schamiloglu is a distinguished professor of electrical and computer engineering at the University of New Mexico in Albuquerque, where he has been based since 1988. His career initially began in nuclear fusion and plasma physics before taking a completely different turn into directed energy microwaves. Today, his research is funded by the US Department of Defense and the US Air Force Research Laboratory, and he is one of the leading researchers in the world in high powered directed energy microwave technology, a field he has spent decades researching and helping advance. This episode is as much about the person as it is about the science. When you listen, you will not just learn about the physics and engineering of directed energy weapons, you will also get a glimpse into the life, the intentions, and the brilliance of the person working behind it. Dr. Shamiloglu's personal and professional story, how he got here, the journey that led him to do this kind of work, genuinely moved me. And I think there are parts of the story that are just extraordinary. I try to cover as much as I could the capabilities of these systems, the engineering challenges, the difference between lasers and microwaves, and where the technology is heading. Think of this as a knowledge journal on a subject that very few people can speak about with this level of depth and honesty. It is one of the best conversations I've recorded on this podcast, and I hope you enjoy it as much as I did. Thank you for being here, and now enjoy the episode with Dr. Edl Schamiloglu. Thanks again. Thank you so much. I'm super, super excited. I have only 83 things to ask you. Hopefully, we can get through them all. But I first sort of like wanted to start with a little bit about like your background, like how you got into working with the University of New Mexico and with nuclear fusion, and then now with directed energy weapons. But before all of that, like what really got you into physics itself?
Well, that's a interesting question. So, it's in my case, it's a very simple answer. I was born and raised in the Bronx in New York, and the high school I went to is the Bronx High School of Science, and that's a public New York City high school. However, it's by examination. You have to take an exam and get a reasonable grade, and then you can get in. So it's very competitive. I barely made it. I didn't make it this much. I barely made it over the bar. And when I was in high school, I read an article in Popular Science about nuclear fusion. And you have to understand those times. This was in the early 1970s,
Wow.
and there was the Arab-Israel Six-Day War. And during that war, the Saudis and the other countries in the areas boycotted selling oil to the United States. So there was a big oil crisis.
Mhm.
And I was a beginning driver back then, and my father had just gotten his license for the first time. We have a car, and I was waiting in line for hours to fill up the car with gas. And I said to myself, this is ridiculous. I mean, it's ridiculous that we rely on foreign oil. It's ridiculous we rely on a carbon-based energy system. And when I saw that article on nuclear fusion, I said, that's it. That's what I will work in. And that's how I got interested in that. So after I graduated high school, I went to Columbia University as an undergrad in the School of Engineering. And I worked in the plasma physics lab, which is a fusion research laboratory. As an undergrad, I helped graduate students. I cleaned up after them, but I also helped build experiments and things like that. And then for my PhD, I went to Cornell University, and I worked on what's called an alternate concepts fusion project. And the actual alternate concept was called a field reverse ion ring. So I learned how to produce a beam of protons and then convert the beam of protons to rotating protons. And the idea is if you have enough current rotating, then the self-magnetic field produced by the rotating protons will reverse the external magnetic field. And that's an ideal way of confining a plasma. So my PhD dissertation was on studying how a rotating beam of protons interacts with the background plasma, slows down, and generates what's called magnetosonic waves. So that was my research. I graduated in 1988, but in 1987, the summer of 1987, I was pretty certain I was going to go to Los Alamos National Laboratory as a postdoc because we were discussing taking my PhD experiment and merging it with a compact toroid plasma. The compact toroid plasmas at Los Alamos became unstable over time. So you generate the compact toroid plasma, it is confined, but after a while, if there is some asymmetry, it may start to wobble, and then you lose confinement. And the idea is if you took my proton ring and injected it into the compact toroid plasma, that would add rigidity to the compact toroid and would stabilize it from tilt instability. So my postdoc was supposed to manifest as taking my PhD experiment, moving it to Los Alamos, and injecting it into compact toroid. But in the summer of 1987, the Reagan administration announced that they will no longer support any research on alternate concepts fusion. And for magnetic fusion, they would only support research on tokamak. So the tokamak is the mainline fusion machine. And so the group at Los Alamos got decimated. My postdoc went away, and I was without a job. But then 2 weeks after that, a professor I knew by the name of Stan Humphreys, he was a professor at the University of New Mexico. He called me and invited me to give a talk. And I said, okay, let me, give it a try. I thought he was looking for a postdoc. But after my talk, I was offered a faculty position. And that's how I came to the University of New Mexico.
And since then, you've been associated with University
Yes,
of New Mexico.
I started as an assistant professor in January of 1988, and I'm a distinguished professor now.
Oh, when I talk to people like you of your stature, it always positively shocks me the decades of commitment or dedication to a certain field, and just like to keep like moving with it, and like because it comes with its own challenges and ups and downs of like grants getting, you don't get the grants that you want,
Right.
or your projects don't get approved and everything, but still kind of like trying to pursue for decade after decade after decade, like hoping that something an idea that you have, that you hold, would work out, or the world will get to see it. It's always like it positively like shocks me, but I guess that is the reason why people like you get to do like work on great things, work on like cool things, and get to achieve certain things. So that's really impressive. By the way, I love popular mechanics, but I thought popular mechanics is something probably like a decade older, like it's a magazine that's only a decade older or something. But now that you say it, now I'm realizing it's like so many years older. I didn't realize that at all.
So there are two magazines. The one I referred to as Popular Science, but we also read Popular Mechanics, and they're decades old publications.
Okay. When you started with the nuclear fusion, when you started in that line, where was the research at that point? Like, what was your research like about, or where was it at that point?
I would say it's there's a common joke in the community that fusion is always 50 years away. But at that time in the early 80s when I started in 81, and it really is nascent research. It's really at the early stages because most of the funding in magnetic fusion was in tokamaks. So those of us who were working in these alternate concepts we're really behind the mainline fusion research. And the reason
Sorry
why,
to interrupt. Can I ask what is the big differentiator between tokamaks and the idea that you were working on?
oh, right. So what a tokamak is it's a toroidal vacuum chamber. It's a toroidal vacuum chamber, and what drives the current and makes this thing work is essentially a huge transformer. So you have this toroidal vessel, and then you have basically a transformer, and that transformer induces the current in the plasma to heat the plasma and to make the confinement. Those of us who are working in alternate concepts were looking at ways of avoiding needing this huge transformer, which makes the device very bulky, very big, very complicated. So the point behind alternate concepts is to have a simpler approach without requiring this huge transformer. That's really what was driving the research. And what's ironic today, there are over 70 startups in fusion around the world, venture-funded startups. And some of them are laser-driven, but most of them are magnetic or magneto-inertial. And what's interesting is most of the ideas are considered alternate concepts. So in simple terms, alternate concepts are fashionable again today after, all these years.
Yeah, but you were saying when you started, like in what position was nuclear fusion, and how is it currently? Now, fast forward to 2026, how much of a growth has nuclear fusion actually gone through?
So actually disappointingly slow. Progress has been disappointingly slow over the decades. It's because magnetic fusion and inertial confinement fusion are very difficult. It's a hard problem. The analogy that's often used to explain magnetic fusion is it's like trying to hold a jello in your hands without having the jello squeeze out between your fingers. So it's a hard problem. I would say that progress has really, really now accelerated since the major breakthrough took place at Lawrence Livermore National Laboratory. So Lawrence Livermore National Laboratory has a facility called NIF. It's the National Ignition Facility. And it was hoped that the National Ignition Facility would demonstrate what's called a burning plasma, over 10, 15 years ago. But they failed. They couldn't do it. They couldn't do it because of physics problems. But after they revisited and reimagined everything, they were able to demonstrate a burning plasma for the first time around 2020. That success, and by what do we mean by burning plasma? What it means is that you produce more energy from the fusion reaction than you do from the laser energy that was hitting the target. All right, that's what it means. But of course, that doesn't include all the energy required to make the laser work and all that. It's just whatever laser light hits the pellet compared to how much energy is generated in fusion reaction. They generated more for the first time. So that was a significant breakthrough, and that breakthrough really, really has lit a spark and caused a lot of investment from venture capital into fusion startups. So now there are, as I said, over 70 fusion startups around the world, most of them in North America.
Okay, so which means experimentally, theoretically, demonstratively, nuclear fusion-based energy is possible, right? It is possible.
Right. And I think the common wisdom is that, okay, the physics of break even was demonstrated, and now you have to scale it to an actual fusion power plant that can get placed on the grid. So now there are still physics challenges, but I would say right now the main challenges have to do with engineering, being able to engineer and accomplish what you need to accomplish in order to have a sustained fusion reaction. I mean, it's still an extremely hard problem, lots of challenges, but there's optimism out there and a lot of venture money coming in to fund it.
Okay. Are there any the technologies that we have, systems that we have that is actually powered by nuclear fusion yet? Anything?
Not yet. No. There are some of the startups are projecting that we'll have fusion power on the grid by 2030. I think that's too optimistic, but let's see. Let them work hard and let them, get at it.
So when you say on the grid, do you mean it could actually cover the electricity?
Yeah. To be on a grid, just like a nuclear fission power plant, just as a coal-fired power plant, or just as a array of solar panels. Yeah, that's the plan. So, some of the startups promise by 2030. I suspect it'll be later than that, but hopefully,
Okay.
in the next couple of decades, we'll actually see that happen. And it's interesting. Do you know a lot of the investment in fusion is coming from these AI companies, because you've heard about all the data centers that are being built and the need for power to sustain the data centers.
Yeah.
They are looking at fusion as a solution to that problem. That's why a lot of the AI companies are investing in fusion.
All right. But it is, in that case, then it is a heavily funded technology, right?
Absolutely. The amount of money. Now, of course, we have 70 companies today. In 10 years, how many will be standing? I don't know. There are lots of issues. There are not only technical and engineering issues, but another big issue is supply chain. If let's say, 5 companies survive and you have 5, scale fusion power plants that are being constructed, there aren't enough components being produced out there, like high energy density capacitors and switches. There aren't enough of them being produced out there to supply those fusion power plants. So there's a huge supply chain issue, and that needs to be addressed as well. So yeah, so the challenges are still, quite enormous.
Okay, so there are there are challenges based on the components availability,
That's right. I mean, one of the bottlenecks is high energy density capacitors. Capacitors used to store electrical energy, and then you release it to either power your laser or to power your, magnets or whatever. So yeah, that's the huge problem.
When you said there are also some limitations when it comes to physics and engineering, is it also because could you mention like a couple? Does it also have something to do with how long the nuclear fusion stays active?
Yeah. So one example I'll give is, I mentioned the NIF facility at Livermore. The NIF facility fires like 36 lasers onto a pellet, and they fire one shot, and then for them to fire a second shot takes probably about a day, because the target chamber is destroyed, and you have to let the components cool. So that's where we are today. For a functioning initial confinement fusion, namely laser fusion-based approach, they're talking about firing it like 10 times a second, or, so now how do you go from needing a day to turn it around to fire another shot to doing it once a second or 10 times a second? That's a huge leap. That's a huge engineering leap. The same is true with one of the concepts at Sandia National Laboratories here in Albuquerque. Sandia has a machine called the Z machine. It's what's called it's a Z pinch. It's basically you're taking 83 terawatts of power and you're putting it through a volume the size of a thimble. That's either filled with gas or whatever, but you make a plasma, and there's so much current that it causes the plasma to crunch. So it's like a cylindrical plasma, and it crunches. And then you put your deuterium tritium pellet inside, it crunches, and it makes fusion reactions. But it takes Sandia about 24 hours to replace the hardware, because after all that 83 terawatts of electrical power generates the Z pinch, you have a lot of vacuum vessels and components destroyed. So you have to, again, to scale that to a working power plant, you need to do it at, once a second or something like that. So again, the challenges are huge. But there's one of the startups is called Pacific Fusion, and Pacific Fusion is building a facility here in Albuquerque. They're going to break ground on August 25th, and they're building $1 billion facility to basically build the next generation machine that's derived from the technology that Sandia National Lab uses, namely the Z-pinch technology. So they're building $1 billion facility, and they hope to have the first, power plant scale device constructed. So again, we'll see.
Yeah. So at some point, I think you switched from pursuing nuclear fusion to directed energy weapons. And the in-between story here is actually this mission called as Sinus 6, which I have never heard of before, that it's a repetitively pulsed high current relativistic electron beam accelerator. Could you say a bit about Sinus 6?
Yeah. So before I go there, let me explain my background. So I arrive in Albuquerque. I arrive at the University of New Mexico, and usually, if you're an assistant professor, you write proposals and you do research on what you worked on for your PhD. I mean, that's the normal, natural course of progression. In my case, I couldn't do that because there was no funding in alternate concepts fusion. So I had to do something else. Well, I was fortunate in that there were two professors at Cornell University where I obtained my PhD who were the founding fathers of the field of high power microwaves. And I was a student there for 6.5 years. So I sat through a lot of brown bag lunches, a lot of seminars. And so I basically knew enough about high power microwaves to basically write a proposal. So here's the interesting thing. To generate high power microwaves, they were using a technology called pulse power to generate electron beams, negative beams. In my case, for my PhD, I was using pulse power to generate positive beams, to generate proton beams. So what I needed was to get a hold of a pulse power generator, and Sandia Labs was very generous, and they gave me one of their machines called a Nereus machine. And so I had a machine. I had structures to generate microwaves. The way you generate microwaves is you basically put an intense relativistic electron beam through a structure, and then in that structure you change electron beam kinetic energy to microwaves, and that's how you generate high power microwaves. And I knew that here in Albuquerque was the Air Force Research Laboratory. Back then, it was called the Air Force Weapons Laboratory. And the Air Force Research Laboratory had a program in high power microwaves. And so I use the word high power microwaves and directed energy microwaves synonymously. They're the same thing. And so back then it was just myself. I had no students. It was me. So I built a solenoid. I got the pulse power working. I got the microwave structures. I built the magnetic field, and I generated microwaves. So I went to the Air Force Research Lab. I went to the chief scientist. I showed him I was generating microwaves, and I'd like to establish a program here. And he was very supportive. And so he shipped $50,000 to Washington to AFOSR, Air Force Office of Scientific Research. AFOSR added $50,000, and I got my first grant from Air Force Office of Scientific Research. So that's how it started. So that
Wait,
was
how do you even just like walk into an Air Force research laboratory? How does it even happen?
I don't know. I figured it out. I don't remember the details, but it wasn't a challenge.
Okay.
Plus, security back then was much looser than post
Okay.
9/11. So things were different.
Okay.
Okay. So that was 89. And then a bit of history. The Berlin Wall came down in November 9, 1989, 11/9/1989. And that quickly led to the fall of the Soviet Union. So in 1991, the head of the Politburo in Moscow was, of course, Mikhail Gorbachev. And Mikhail Gorbachev was introducing glasnost and perestroika. Glasnost in Russian means transparency. Perestroika means restructuring. So he wanted to kind of open up society, and so what was happening in the scientific world is we were getting exchanges between Soviet and Western scientists. So one of the vice presidents of the Soviet Academy of Sciences, his name is Gennady Mesyets. He visited the University of New Mexico in 1990. And why did he visit the University of New Mexico? Well, it turns out that he was friends with my dean at the time, Jim Thompson. He was also friends with Professor Christensen at Texas Tech University. And he was also friends with the chief scientist at the Air Force Research Laboratory, Art Gunther. And so all three of them knew Gennady Mesyets. So he visited us, and during the visit, he offered to sell us their CNUS, one of their CNUS accelerators. CNUS is an acronym for Sinotochny Uskoritel, which means high current accelerator in Russian. So CNUS means Sinotochny Uskoritel, high current accelerator. And so at the time, the Air Force Research Lab offered to support that. So in the summer of 1991, I was supposed to fly to Siberia and negotiate the purchase of the device. Well, again, if you remember history, Gorbachev was overthrown during a coup in August of 1991. But that coup only lasted about 6 days. And after that, it fell apart. Boris Yeltsin became very popular. And so Gorbachev was reinstalled in Moscow. So my trip was canceled because of the coup, but then it got put back on. So in October of 1991, I traveled to Moscow, and then from Moscow to Tomsk via Sverdlovsk. And so I got to be in Academician Mesyets' home in Sverdlovsk, which is now Yekaterinburg. And then from Yekaterinburg, I flew to Tomsk in Siberia. And I had studied Russian in high school and at Columbia University. I was in the advanced literature class. So we negotiated the acquisition in Russian. And so then I came back in October of 1991, and it was delivered to my lab in July of 1992. And another interesting footnote is Susan Eisenhower, who is the granddaughter of President Eisenhower, was part of a company that at the time was handling the import of former Soviet technology. So her company handled all the paperwork in getting the device to us here in New Mexico. So yeah, so then we commissioned that device, and that accelerator made my career because it was very reliable. We could take a lot of data, and it was just a workhorse.
Okay, first of all, you knowing Russian, I'm guessing, is one of the reasons why they decided to send you. What are the other reasons? Like, how did you get to do this?
Well, that's one of the reasons, but I was the only one here that was behind building a program in high power microwaves.
They could make a movie out of you.
Oh, no.
Seriously, like just
No.
you're not going from nuclear fusion to directed energy weapons inspired by two professors at the university, and then you building your own thing without any students or anybody, you mission building your own mission, walking into Air Force and then going to Soviet Union to collect this. It's a movie. This
Yeah.
is wow. I'm really fascinating. But I want to ask you, so what is the significance of this mission? Given you said before you even went to Russia, without you actually built like a directed energy microwave weapon by yourself, right? So what is the significance of CNS 6 then?
Just to clarify, I did not build a high power microwave weapon. The military would like to use it as a weapon. I built a high power microwave source for researching beam wave interactions and learning the physics and improving the operation of the device. That's what we do. Everything we do is basic research. It's publishable research. We don't do any weapons research. It's all just basic physics and engineering research. So I did have a machine that Sandia gave me. It was the Nereus machine. Unfortunately, it was not a very reliable machine. We could perhaps take 6 data points a day, and then inevitably something would break, oil would leak, or there would be some problem. So it was very cumbersome. The beauty with the CNIS is that my PhD student at the time, so by the time the CNIS arrived, I already had my first master's and PhD students. So when it arrived, my PhD student can take 600 shots a day instead of 6 shots a day. That's huge because when you have so much data, you can really, really perform careful computer simulations and compare your simulations with your data. When you take 6 shots a day, you really can't do that. But when you take 600 shots a day, you can. So it's the capability of taking so many shots a day, generating so much information that really gave us an edge.
Okay. When you got the CNS 6, what did you understand from that machine? What breakthrough did you kind of like have by studying that machine?
Okay, so I'd say the first scientific breakthrough we had is the following. So the tools we use to simulate the performance of these devices is called particle in cell code. So what a particle in cell code is, it is a finite difference time domain electromagnetic simulation that is fully integrated with relativistic kinematics. So in traditional finite difference time domain electromagnetic simulations, all you are doing is you're calculating the electromagnetics. By integrating it with relativistic kinematics, you're also able to understand how electrons and electromagnetic waves interact. At the time, in the early 1990s, these tools, these computational tools, did not do a good job of simulating the performance of the device. In other words, the folks running these codes would simulate a device. We would show our data. The simulation would not agree with the data. They would then tweak the simulation, and then the simulation would agree. But then if we did a new experiment and a new simulation, they would disagree. So this was a major impediment to progress. Well, it turns out that one of the scientists at the Air Force Research Lab his name is Brendan Godfrey. He had written the algorithm that was common in these particle and cell codes to beat back or to damp numerical noise. And he gave us a heads up. He said, why don't you take a careful look at that? So I collaborated with a colleague at Sandia Labs. His name is Ray Lemke. He would be running the particle and cell simulations since we did not have that capability at the time. And so what we decided to do is we decided to first perform very vanilla experiments. And then we'd perform the particle and cell simulations. And what we decided to do is we would adjust how much numerical damping we invoke in the code. We would adjust it until the code matched the experimental results. And by that, I mean when the code calculated power matches the experimentally generated power. And then we never touched that. And then we did some crazy experiments. And what motivated the crazy experiments? Well, what happened was about a year after we received the CNS accelerator, we noticed that the power that we were generating kept decreasing over time. And we couldn't figure out why that was the case. So I communicated with my Russian colleagues, and then two of them flew back to Albuquerque, and they looked at the situation. And what they did is, they opened up the system and they looked inside and they took a wooden dowel and they took a hammer and they took the electromagnetic interaction structure. It's called the slow wave structure. They took the slow wave structure and they hammered it really, really hard. And then we closed up the system again. We put it under vacuum and we took data. And lo and behold, we went back up to the original power levels that we had achieved. And so I was curious. I asked my colleague, I said, Kolya, why did that make a difference? And his explanation to me was, well, after you fire many shots, the electromagnet that's used to confine the electron beam causes mechanical shock. That mechanical shock causes the structure to loosen. And therefore, you don't have as good an electrical contact as you originally had for the return current to flow back. And I didn't buy that explanation. That explanation made no sense to me. So I told my student at the time, Larry Moreland, I said, Larry, let's intentionally introduce the effect of loosening the slow wave structure. So I told Larry, let's build these thin rings, millimeter thickness at a time. And why don't you go ahead and insert a 1 millimeter ring to show that it's loosened up 1 millimeter, insert another ring and take data, and so on and so forth. And then we got our data, and I was amazed that, originally with no rings inserted, we had 100% of the power. But then after only one ring, we dropped to about 50% of the power. And after like 2-3 rings, we're down to 10% of the power. And that's when my Sandia colleague came. He did the simulation. That's what I meant by doing these crazy experiments. We're doing these experiments where we're inserting rings. And Ray simulated that. And then lo and behold, his simulation results matched our data perfectly. And that was the first time a particle and cell code and experiment agreed a priori without making any tweaks. And so it's the fact that we understood what was causing the mismatch was the numerical damping factor not being properly set for our experiments. And it turns out that the code that we were using, the Sandia code, was used at Sandia Labs primarily for low-frequency phenomena. They were studying what's called magnetically insulated flow. And the frequency there that they were concerned with is 200 megahertz, so 200 million hertz. the frequency that we generate in our experiment is 10 gigahertz or 10 billion hertz. So what was happening is the damping that was used in the code didn't affect the low frequency phenomena, but did affect the high frequency. So we had to back off on that damping to allow our high frequency simulations to be, consistent with the experiments. So, so we published the very first paper where you have an agreement between a PIC code, particle and cell code, and an experiment. And of course, today, the particle and cell codes, there are many commercial codes, are amazing and are do an excellent job of simulating our devices. So that was our first real breakthrough. And the reason why we were able to achieve that is because of our ability to take 600 shots a day. We just had so much data. We could put a data point, which is an average of 20 shots. We have error bars. So we were able to do very precise measurements.
Yeah. So which means back then, where during your experimentations or even now, something that a criteria that is very important is that no matter how many amounts of pulses, the speed of each pulse, the temperature should always remain high. You want to prevent it from like dropping it.
Not quite sure what you mean by temperature.
Like you meant like the free, like you want it to stay high. You don't want it to come.
Oh, yeah, that's the power. That's right. We
yeah.
want. That's right. So the metric we use is how much beam power ends up being radiated as microwave power. And so the idea is, of course, for a given voltage and current, for a given electron energy and current, you want to make sure that you have as high a power as you can get, because that's the name of the game, to go higher and higher power.
Yeah, is it right to call this like a pulse generator, this type of machines like Sinus 6?
Yeah, the Sinus 6 is a pulse power generator, yes. It's based on Tesla transformer technology. There are others that are based on what's called a Marx generator technology. And what pulse power is it's basically the following. The analogy I like to use is, imagine you have a bucket and you want to fill your bucket with water. You get a hose and you fill your bucket with water, and it may take a couple of minutes to fill the bucket with water. But then if I had a button on top, and if the bottom of my bucket opens, all the water gushes out instantaneously. That's what pulse power is. You accumulate electrical energy gradually over time, stored in capacitors, but then you release it very, very quickly, because power is energy divided by time. So if you have the same amount of energy, but if you release it in a shorter time, the denominator is smaller so that the power is higher.
Okay. But now that you have better pulse generator systems that can perform beyond what Sinus 6 is, I'm guessing it is still there in the University of New Mexico, this particular machine?
Yeah. Yes, absolutely. And of course, the laboratory where it was produced is called the Institute of High Current Electronics in Tomsk. And they of course, over the years have advanced the technology. They had the Sinus 7. They had very, they've developed these generators with higher energy, higher power, and longer pulses. But for we're not interested in developing the generators. We just use them to study the physics of generating high power microwaves.
Okay. So if this was, so you said you went and collected it in 1991, right?
I went there to negotiate it in 91. It arrived in my lab in 1992.
Yeah, which means Soviet Union has already probably been developing that like a decade or like probably more than a decade, right?
Yeah, they were developing those since the 70s.
Wow. Okay, so and what was their intended purpose? Which means were they already using microwaves, directed energy microwaves? All right, just a quick pause from the episode. If you're enjoying the podcast, I really appreciate you rating it on Spotify, subscribing to the YouTube channel, and sharing the episode with someone who you think might enjoy it. Feel free to drop a comment right here on Spotify, what you liked, what you didn't like, or any thoughts or no's you have for Dr. Schamiloglu or for me. Everything you see and hear on this podcast, from scouting, researching, hosting, producing, editing, distributing, is done entirely by me. So every like, subscription, rating, and share genuinely makes a difference. Thank you again for listening. And now I'll let you get back to the episode.
Yeah, I mean, so the group in Tomsk that I was, by the way, we were very close, very good friends. We had a very strong scientific collaboration until the early 2000s. And of course, Putin came on board in like 2000. And after that, things got really, really, the FSB, which is the follow-on to the KGB, was back at the institutes. Things got bad again, so our collaborations ended. But we had a golden period between 1991 and about 2000 where we published numerous papers together and we collaborated.
Yeah. So for me, as someone who's not obviously in the field and everything, and because for people like me, it's only now, maybe for close to a decade or something, we are hearing some things about like this direct energy weapons and all those kind of things. So it's very surprising to, it's shocking to hear that, like Soviet Union has been working on this since like the 60s, early 70s or something.
Yeah, so actually, yeah, high power microwaves started in the late 60s,
Okay.
both in the US and in the Soviet Union.
Yeah.
And of course, you know, there are wide variety of applications. Like high power microwaves are used to heat fusion plasmas. High power microwaves are used in accelerators to accelerate particles. And of course, high power microwaves can be used as a counter drone, counter UAS, because the very high power levels go hand in hand with very high electric fields, which can disrupt the circuitry and the chips in electronic objects. So yeah, I mean the military is interested in high power microwaves, for that reason. But there are many other applications.
Right. Yeah. Of course. But from that time onwards, when you started working on microwaves and up until now, like, do you recognize how much, like, do you recognize, or do you sort of, are you able to speak about how much the development has actually progressed from that time, from this onwards? Like, could you speak a bit about, like, in terms of like the engineering or the capabilities that if we had like in the 70s and up now, like what big advancements are you talking about?
Yeah. So I can talk about like three phases. Like the very first phase is what we refer to in our book is the high power microwave power derby. So this is when the first publications in high power microwaves started coming out, and here we're talking about the late 60s and early 70s. And there at that time, scientists in the US and in the Soviet Union were working on comparable things, on comparable technologies. And so what would happen is one year, the US would publish they achieved a certain power level. The next year, the Soviets would publish that they generated more. And that went on from like 1970 till the early 1990s, where it was this constant power derby. But then that power derby ended. Why did it end? Because uh, so much power was being generated that if you tried to generate more power than that, something would fail. You would have so much electric field, because if you have very high power, you have very high electric field. And what the high electric field causes at very high power levels is like a breakdown, an electrical breakdown to occur. And that's referred to as pulse shortening. So there was a lot of research invested in the mid to late 90s on understanding pulse shortening. And inevitably, pulse shortening had to do with there being so much high power that you would have plasma being emitted from surfaces, and that plasma would disrupt further microwave generation. So that was the second phase where people were looking at pulse shortening. After that, the community realized, well, maybe we're generating enough power, don't try to generate more power, but maybe try to generate a high power at a certain repetition rate. In other words, repeat it, 10 times a second or 50 times a second. So that's where things shifted. And, you may ask, why did the Soviets develop the Tesla transformer technology and the US didn't pursue that? I think my answer to that would be, at the time, in those years, in the US, these systems were intended to be laboratory-based systems. If you have a laboratory-based system, you don't care how large you are, you don't care, you have plenty of space. And so, but the Russians, I think the Soviets, back then were thinking of applications in their mind.
Mm.
And these Tesla transformer systems are can be more compact and mobile. I mean, back then they had used these compact CNIS machines in mobile systems. So that's what was driving that. But of course, I would say that applications were really, really nascent at the time as well. I think one of the uh, one of the large applications that was driving things in the 2000s and early 2000 teens was, motivated by the Iraq War, where you had improvised explosive devices. And so in the DoD, they were trying to see if you can use a high power microwave system to pre-detonate an improvised explosive device. And they actually fielded systems in Iraq to test that capability. But now, of course, ever since the Ukraine war and now with the conflict in the Gulf, the pervasiveness of drones has, caused, I think, both high power microwaves and high energy lasers to emerge as strong candidates for possibly countering those threats. And so maybe the golden age of application of high power microwaves has come.
Mm. I sort of want to split the discussion into high-powered lasers and high-powered microwaves. So from what you've told me so far, am I right in understanding that it was high-powered microwave that was started with first, and then later on came high-powered lasers? Is that right?
No, I think that, the laser, so high power microwave started because of the capability of pulse power coming on board, and that was the late 60s. The first laser was in the early 60s, around 1960 or so. And I think even back then, the military looked at the laser and immediately thought of how can we weaponize this. The laser, high energy laser evolved in, I would say, 90s and 2000s. And there, the laser technology was called a high power gas laser. So it was a laser where the lasing medium was a gas. Now, it turns out that here at the Air Force Research Lab, they actually had a demonstrator called the high energy laser, which was a Boeing 747 aircraft where the laser would come out of the nose of, and the application there would be this 747 it's called the airborne laser. The 747 with the laser would be used as a missile defense technology.
Right.
But after 2010 or so, the Air Force realized that having these harmful gases, these really, really bad gases on a Boeing 747 in flight in a military conflict was not a smart idea. So the Air Force abandoned this gas laser program. So they completely got rid of that. And then in the 2010s, they shifted to using glass as a lasing medium, and that has led to what's called fiber lasers. So fiber lasers are the technology that are being used for the high energy laser. And of course, the amount of power generated by the gas laser was much higher than what's generated by a fiber laser, but they're pushing the technology today such that today, 100 kilowatts is being generated in these fiber lasers.
Right. So I want to understand something, just like talking about lasers at the moment. So if, let's say, if I have to, like, break open like a directed energy like laser machine, what is exactly the source of that power? Like, what's exactly the system that, what's the source of the power basically? If I have to break open,
Well,
how does the supply chain basically look like?
yeah, I mean, so again, I'm not an expert in lasers, but uh, both directed energy microwaves and directed energy lasers, ultimately, the prime power is electricity. You start with electricity. And once you have electricity, you go to high voltage.
Mhm.
And once you have the high voltage for directed energy microwaves, you accumulate electrons in high voltage, and then you switch it and you generate these high power pulses. For the lasers, they use the high voltage to drive lasing inside a medium. In the case of fiber lasers, the medium is glass. So you convert electricity to photons, and that's how you end up generating the high energy lasers. In microwaves, you convert electricity to microwave frequencies. And it turns out that the efficiency of converting electricity to microwaves is much higher than the efficiency of converting electrical energy to photons. Photons inherently are very low quantum efficiency, so that's the big challenge with lasers, is generating as many photons as you can for a given amount of electricity.
And this laser can basically cut through metal, steel machines.
So the way,
Slice it.
yeah, so for these high energy lasers, there are several factors. But in the end, the way it would work is by physically putting a hole into your target. So it's going to put a hole into your target, and then your target will fall out of the sky. Now, your ability to use a laser to put a hole in your target depends on many things. It depends on how far away you are.
Yep.
It depends on the atmospheric conditions. If
Right.
there's dust or rain, that's a problem. It depends on what's called dwell time. Dwell time means how long can you stay fixed at the same point on the target. So there are many, many factors involved in being able to be successful. Microwaves, in that sense, are a little bit less vulnerable to atmospheric conditions than lasers are. Lasers are much more vulnerable to atmospheric conditions.
Okay, so laser is something where you point and you hit, but a microwave is where you kind of create a shield in the atmosphere, right?
Yeah, so the way to think about it is all of us have seen a laser pointer. All of us have seen Star Trek and Star Wars, so we all know how a laser looks like. So a laser beam is very tightly collimated, and yes, the military actually really likes lasers because it's like a kinetic weapon. In other words, it's like firing a missile, because you can look and see whether it worked or not, right? You can see
Right.
the laser hitting the target, and then you can see the target fall out of the sky or not.
Right.
With microwaves, you can't do that. So the microwave beam is a very broad beam. When it leaves the source, it is, we like to say it's diffraction limited. So it turns out getting diverging and diverging and diverging. And, you know, and the way it works is you don't see smoke. You don't see, if it's a drone and if it falls out of the sky, then you were successful. If it's a drone and it doesn't fall out of the sky, you were not successful. And you don't know why you were not successful. And I think this drives the military crazy because with lasers, it's a sure thing. It's a yes or a no. It worked, it didn't work. With microwaves, they speak in terms of probabilistic, probabilistic curves. What's the probability of effect? And the way they talk about it is there's a 70% chance that 30% of the targets are hit, and that drives the military crazy because they don't like that.
Okay, the reason why you're saying the current microwave system has a limitation, is it because when you power the system and when the range becomes like broader and broader, when it like expands, does it mean that maybe parts of area has strong power and there are parts of area with low power? Is that the reason?
No, it's pretty uniform. I mean, as it expands, as it diverges, what happens is the power density decreases, which means that the electric field decreases,
Okay.
and if the distance is too far,
Okay.
it will have diverged so much that the power left at any one point is lower and would be ineffective.
Okay.
The the advantage of having a diverging beam is if you have a swarm of drones, let's say you have 200, 300 drones coming at you, with a divergent beam, if you're within range, you can just scan and then take out all of them. Whereas if you had a single laser system, you have to point, track, shoot, and it's very difficult to go after hundreds of targets with one laser system. So that's an advantage for the microwaves.
Yeah. Okay, this will be a very stupid question to you, but I have to ask. So, when you are shooting a laser or when the microwave beams out the energy, so it's basically an electromagnetic wave, right?
Yes,
And
both of them are electromagnetic waves.
what is the energy there? What is the energy? Is it just electromagnetic energy, which then converts to heat when it hits the target?
Okay, for microwaves, it's the electric field. It's the electric field, it's the high electric field that couples with the target that causes current surges inside the device and would cause a component to either temporarily fail or to permanently fail. With lasers, it's actually a thermal effect. You actually are heating something. So it is the thermal effect of the laser that's doing the work. For the microwave, it's not the thermal effect. It's just the very high electric field that causes basically the electronics to get disrupted.
Okay. These are some limitations that I perceive. Let me know if if you see this as well, or if obviously. But I just wanted to understand. So when talking about a laser, the range obviously matters, right? Is there a limitation in terms of like how far the laser can stretch?
There definitely is a limitation. I mean, again, uh, what ends up happening is if you have the longer you travel, uh, you're going to attenuate the laser because of things like turbulence in the atmosphere, things like particulates in the atmosphere, or what have you. You really are going to attenuate. So definitely there is a finite range. I don't know what the effective range of these things are in lasers, and the military doesn't talk about that. And the same is true with microwaves. There's you always want to you always want to be able to do this as far away as possible.
Right.
But the price you pay when you're far away is it has to travel more, it diverges, the electric field goes down, and your chances of success go down. So yeah, so it's a balance.
And also you were talking about how when in turn I'm sorry I'm sticking with laser, but I will get into like a microwave, but I want to just ask as many things as I can about some limitations that I perceive. So you because you briefly mentioned that another weakness about the laser is that it can only shoot one at a time. Then you have to move the direction, and then you have to shoot it, and then you have to move the direction, and then
Yeah.
but what if it's like multiple things like coming on? Is there a way to like shoot multiple lasers at the same time?
You'll need multiple laser systems. I mean, you'll need multiple independent laser systems to be able to handle, and then that starts getting costly.
Yeah, I'm guessing this is invisible for an enemy. Would this ray be invisible?
No, so these are in the infrared part of this electromagnetic spectrum, so they are not visible.
Okay. And what because you also mentioned due to some atmospheric conditions, could there be a problem? When it rains, there's cloud, there is dust. Could it
Absolutely.
somehow be?
All of those are a problem for lasers. I mean, yeah, the ability to use a laser. Also, if you're in a littoral environment, and by that I mean if you're near the ocean or the sea, the humidity is very high, and that affects laser propagation as well. So yeah, so lasers are very, very much affected by weather conditions.
Okay. And in terms of like a microwave, which you're working on, is one of the limitations also about like how far the electromagnetic field can stretch?
Yeah, as I said, the power goes down as 1/distance squared,
Okay.
and so the more you propagate, the lower is the power, and power is related to electric field, and if your power goes down, your electric field goes down, and therefore your ability to be effective gets disrupted.
Yeah, and also I'm guessing also the range as well, right? Like how the distance between the electromagnetic shield and the actual generator itself. There should be a bit of distance, right? Because you don't want the enemy drones to come too close to the
Right.
range.
I mean, yeah. I mean, so in terms of if you had a ground-based system, let's say, and you fire it, there's no issue for the people around because they're in the back of it. But again, you want to have again, it's a trade-off. You want to have as um, much of an effect as possible, which means you should come as close as possible. But then again, you don't want to be as close for other reasons, and so it's a balance. It's a balance.
Can I ask what are some of the engineering problems or like just like the capability problems that you're trying to solve?
So in my laboratory, we're focused really on uh, how to increase the efficiency of converting electron energy to microwave energy. That's what we do. That is the only thing that we do. Because if you can make, as an example, we took one high power microwave device called the relativistic magnetron, which is very similar to what's in your microwave oven, except much higher power levels. And we took the efficiency from around 25%. So by that I mean efficiency of, for a given amount of electron beam power, how much microwave power do you make? Uh, if you were 100% efficient, all of your beam power would be converted to microwave power. So for the relativistic magnetron, we took it from 25% to over 70%. So that's good because then you're more efficient. Now, in terms of taking it out of the laboratory and into the field, there are other considerations. For example, uh, these days there's a lot of work going on how do you make the pulse power smaller so it could fit on more compact platforms? How can you make the system more efficient by, for example, instead of requiring a magnetic field, perhaps have a lower magnetic field so that you don't need as big a magnet to power the system. Those are the engineering considerations because and being able to do that really, really depends on how components are improved. I mentioned high energy density capacitors previously. I would say today, the size of a capacitor that is, for example, like a textbook, uh, was about the size of a garbage can, 30 years ago. So, as more and more advances are made in capacitors, and as capacitors become higher and higher energy density, then they take up less and less space. So you can build these systems so that they can fit in more compact platforms like unmanned aerial vehicles and so on and so forth. So that's really where the engineering is going, to be able to make these drive the pulse power drivers, making them smaller and lighter. That's where the engineering push is happening.
Yeah. Do you see at some point in the near future where it switches from being manhandled to becoming autonomous?
Yeah, I can see that. If we're not already there, I certainly see that coming, because the issue about making it autonomous is not really the challenge. The challenge is being able to package these uh, in form factors where they would fit in a reasonable sized.
In a drone or in an aircraft or
Yeah,
something?
exactly. That's right. That's where the technical challenge is. I think the autonomous part of it is not that challenging.
Yeah. I'm guessing the more powerful these systems get, right, be it both laser and microwave, another challenge wouldn't it also be able that it should be able to differentiate between an enemy drone and its own national drone, right? Because you don't want to go shooting everything that you see come across.
Absolutely. Absolutely. That is a concern. And there, again, the challenge is that the pace of technological evolution is very, very fast now. In so so you know there could be new classes of drones coming onto the field or coming to a theater that one has never seen before. So there has to be a way of tracking and understanding whether the drone is a friendly drone or not a friendly drone. And that's not a high power microwave problem. That's a completely different, that's an intelligence and, you know, uh, just data acquisition, data analysis problem.
Right. This might be another stupid question. Will there be sound in a microwave when in the electric and the electromagnetic field? Is there sound?
There's no sound in the electromagnetic wave, but there is sound when one of these machines fire, because every time you fire, you have switches that close. And so for example, in the CNIS in my laboratory, before we take a shot, we clear out the room, everyone's out, we close the gate, the light is flashing, and the only thing you hear is something like that. That's the sound of the switch after you fire. That's the only sound you hear. Um, if you had a system that had all solid state switches as opposed to a gas switch, that system would be much more quiet, much more silent.
Okay. This might be another. I don't know if you have like thought about it. So if they are building a system that can like shoot create an electromagnetic field or shoot an electromagnetic laser, wouldn't shouldn't then you also think about a countermeasure in the sense that to shield yourself, is there a way to sense something and protect yourself from these kind of lasers and electromagnetic
Yeah. So,
microwaves?
the U.S. DoD funds programs in what's called CDEW, CDEW. That's counter directed energy weapons. And so, if you took your target and if you completely covered it in aluminum foil, then that's a Faraday cage, and then the microwaves would have absolutely no effect.
Mm.
Now, the trouble is, if you have a target, which might be a drone, that drone needs to communicate. So you need to have an antenna. It needs to have an antenna, an antenna for GPS. And so therefore you cannot perfectly shield it, because if you perfectly shield it, you lose your GPS and you lose your communications.
Yeah.
So from a practical point of view, no, you can't do that. You can try to do a better job of shielding your components, for example, sensitive electronics. But every time you try to do that, you'll probably add weight. You'll probably, So then the question is it's a balance of how much do you invest in trying to harden your system versus how effective it can be. And there are also technologies for counter lasers. There are coatings that are being developed to make things less pervious. But I think all
Maybe
these
to detect a laser or something.
yeah, it would be to deflect the laser or to diffuse the laser to decrease the power density so that it doesn't generate as much heat as it was intended. And all of those approaches start making sense if you have a expensive, complex system that you're trying to defend against. But if you talk about trying to defend against drones that cost thousands of dollars, these counter DEW strategies don't make a lot of sense.
Yeah, but you know what? The thing is that I think it's a long. Don't you because you said that we can cover it with aluminum foil, but then you can't cover everything. Maybe you can only cover like small components of it, but only till you guys figure out how to actually cover it without affecting the GPS system or something, right? I mean, it's all part of like technological progress, correct?
Yeah, but you can't, your GPS and your communications need an antenna, and
Yeah.
that antenna needs to be unimpeded. And that antenna acts as a perfect receiving antenna for the microwaves.
Hmm. Yeah. Okay. I'm a little bit. I'm just kind of a little bit skeptical in the sense I feel like both the countermeasure as well as the directed energy measures as well through laser or microwave. I mean, I think you also agree. I think there would be a lot of advancements, right? There would be like the more aggressive the countermeasures become, then I think the more aggressive that you need to become in terms of like
Sure.
your development.
As I said, there's investment in programs
Yeah.
for counter-directed energy weapons. It's again, that's not an easy problem.
Right.
One of the things that killed Reagan's Star Wars, the Strategic Defense Initiative, one of the things that killed it was, the Strategic Defense Initiative was supposed to be these, lasers in space, or, ground-based lasers being shot up into space and everything, to kill a ballistic missile carrying a nuclear weapon as it reaches the maximum and starts re-entering the Earth. One of the things that killed it is you can disable that system really, really easily by throwing a rock at a mirror in space, right? You need a mirror and if you just throw and they call those things smart pebbles. You just throw it at the mirror and you destroy the mirror. Okay, so you have a very expensive system up there, but it takes very inexpensive things to destroy it and to make it less effective. So that was the big Achilles heel of Star Wars back then. But again, there's work being done on counter-directed energy weapons. It's still, it's not an easy problem.
Right. Obviously, I mean, nothing that is going on is actually easy. Nothing that you spoke about. It's brilliant, honestly. So you were actually. I want to touch quickly on the Havana syndrome subject.
I prefer we not go there.
Okay.
If that's okay with you. I have
Okay.
I have to not speak to that.
Okay.
But
All right.
I think what I would say is that I think the jury's out still on that, and I think one day there will be a smoking gun and the matter will be resolved. But until then, I can't speak to that.
Are you comfortable in terms of speaking about how these can actually be used to directly impact a biology, like a human sensory systems, etc.?
I have my opinions based on facts, but it's not something I would be able to share. All I would say is the mechanism has nothing to do with thermal effects. So, for example, when the Havana syndrome was first reported and they interviewed biomedical engineers and they talk about it, they always assumed it would be an effect similar to your microwave oven. The way your microwave oven works is actually by heating. Your microwave oven works by the water, the liquid content in your food or whatever it is, and it heats the liquid, and then the liquid heats the rest. So if you took a roast and you put it in your microwave oven, it heats from the inside out because the microwaves penetrate to the inside, and because of the imaginary part of the permittivity of the water molecule, it heats it up, and then it transfers the heat to the external. But whatever Havana syndrome is, it has nothing to do with that. It has nothing to do with microwave heating or anything like that.
Right. Now, when talking about like laser or microwave, we are talking about electromagnetic field, a field here, right? Or electromagnetic
Electromagnetic energy, yeah.
energy. So, is it possible to actually also through this technology to actually also have a different type of information, like let's say like a sound or some sort of information to pass that kind of an information?
Um, so I know from the microwave side, there is, something called the Frey effect, Frey, where if microwaves interact with the human ear, you can hear sounds. Again, I don't think Havana syndrome has anything to do with that. And with
No, I'm
lasers,
not talking about Havana syndrome
oh,
at all.
okay.
But I was just asking, could you, in terms of like laser or microwave, could you inject a different type of information in this field, like for example, like a sound or a message or something?
Uh, well, so the way, for example, TV and radio transmitters work is you have a beam of RF, electromagnetic energy, and then on that you have a carrier wave,
Right.
and the carrier wave is what carries the information. So yeah, if you have a beam and if you modulate it, you can carry information on it. With lasers, I'm not so sure. There might be ways of coding information in lasers, but I am less familiar with that.
Okay. Professor, I have to ask you something. I always kind of, because I try to educate myself on such different subjects. I have for a very long time operated with this belief that there are things that are possible in the name of physics, science, engineering, technology, etc. that is like way out there that people like me, like who are part of like the general public, are just like not aware of or something. So a lot of things that we think is as like, it's science fiction. Hey, this is not going to be possible at all. I kind of operate with in the framework that there are things out there which are being like suppressed. Maybe it could be because of national security, because you don't want your adversary to know about it. It could be your control or something like that. Do you also kind of share that idea that, hey, like you don't have to go into the details about it, but just asking, hey, there are things out there that it's just not visible in my textbook that I studied in school or college?
Well, I think as the scientist, you're always humbled by what's out there and by how little we really know about everything. I think that um, that's the beauty of how science works, right? Science, you end up having a hypothesis, and you believe that hypothesis to be law, uh, because it's verified by experiment. But then maybe one day an experiment will come along that will disagree with that hypothesis, in which case you have to throw it out the door and come up with a new one. And so, yeah, I think there's, constantly evolving knowledge. Sometimes the more you learn or the more you discover, the more you realize how much you don't know. So, yeah, I think that is the case.
Yeah. Just the last 2 minutes. Your research is actually directly being funded by the Department of Defense, by the Air Force, etc. So, based on all the research that you've done, do you actually get an oversight about like, okay, where exactly it's used, where your research is being used, or anything?
Absolutely not. I mean, I think so in DoD language, the research we do is called 6.1. 6.1 means it's the most basic level of research. And then as you go to 6.2, 6.3, it becomes more applied. And then as you go to, higher, like I don't remember what the highest is, 6.7 or something. There you're talking about a real system that's going out in the field. I think we're graded by our sponsors on whether any of our basic research advances transitions into the labs. So, we don't see what happens after it transitions to the DoD laboratories where they would use it. But I do know that several of our advances have made it into systems in the DoD, which is good for us. But we never see where things go really.
So does this mean there could be some groups who's in 6.7, 7.0 levels actually going on around there?
Yep, absolutely.
Right. Uh,
Don't forget, I always like to say, again, your simple pencil.
yeah.
Your simple pencil can be used to write poetry. It could also be used to design a nuclear bomb. So
Right.
it's.
Yeah. Can I ask, obviously, if you have brought yourself this far with your work and with your research and everything, there is obviously this innate curiosity, drive, passion for science, physics, and everything. Could you slightly say about that? Like, what is it that still keeps the spark alive? Like, what really drives you in terms of like the curiosity that you have? Is there something that you want to prove? Is there something that you really want to create in the time that you have?
Uh, no, I mean, I wouldn't say there's. I think I'm just fortunate in that I have a job where I earn a salary, where I enjoy what I do. I go where my curiosity takes me. I don't have any one goal per se. I mean, I've overseen 44 PhD students, 44 master's students, and they're all out there in the labs doing great things. One of my former PhD students, Kelly Hahn, she actually measured the neutron yield on the uh, uh, burning plasma experiment at Livermore. And she's on all the papers that came out, and she's on the prize that team was awarded. So I'm very proud of them, and I think just continuing this until I can continue it no longer will be my goal. In other words, I enjoy what I do, and you know I don't have any one thing that I want to accomplish.
Has it ever hit you like where you had to like face the fact that hey, the things that I am creating might at some point be used for, because you just said with a pencil, right?
Yeah.
We can be, it can be, what you're creating can be used to create poetry, but it can also be used to create like a weapon. Have you
Right.
made your peace with it, like when you had to like deal with the idea?
Again, the uh, I don't have any problem with the high power microwave technology being used as a counter electronics application, because that is a defensive application, and if it can benefit, I like to say that despite all the difficulties in my country, uh, I'm a first generation born in the United States. And, my dad was a refugee from the Soviet Union. He ended up, after World War II, stateless. He didn't want to go back to the Soviet Union. No other country would take him. But he came, the United States took him. And for that, I owe a debt of gratitude. So if I can contribute to the security of this country, I am more than happy to do so.
Right. Professor, I don't study under you or something, but you're brilliant. Like you're really, really brilliant, and thank you for sharing your natural born skills and your developed skills and your curiosity with the world and everything. You're your story could hopefully will one day be made into a movie or something. This guy goes and knocks at the Air Force research laboratory and say, I have a machine here, and you go to Russia to pick up a machine. It's amazing. It's really, really amazing. Very, very often, more often, we always get to hear things about these kind of research work, always from somebody from the Air Force or somebody from the Department of Defense who would not have the real knack or understanding or to say, hey, this is the physics behind it, this is the engineering behind it, these are the things that I'm trying to solve. So, but to directly hear from someone who's very like physically like involved, who's handling these things, it's really an honor. It's really, really an honor to talk to you. I'm really, really grateful for your time.
Thank you.